Hey everyone, let's talk about Newton's third law, and then we'll do some examples where we apply all of Newton's laws. So, what Newton's third law states is that for every action force, there is an equal magnitude force in the opposite direction acting on a different object. So, a force that's acting on an object is always the result of the interaction with another. And in other words, those forces come in pairs. For example, you can't pull on a doorknob, without the doorknob pulling back on you. And we're going to examine the situation of kicking a ball. So when you kick a ball, your foot exerts a force on the ball to move it forward, but your foot, definitely feels something happening to it too, right? Which implies that there's a force acting on your foot from the ball itself. Like when you kick a ball with no shoes on, you definitely feel the ball putting a force on your foot. So mathematically, Newton's third law is simply stating this. If we draw a free body diagram of us and the object that we're interacting with, then Newton's third law states that there's a force that's acting on us from the other object, and that is equal and opposite to the force of that object acting on you. Okay, same magnitude, different direction. So let's look at that situation, right? You have your foot kicking a ball, and when your foot hurts as a result of the kick, well, that pain is a result of the force of the ball acting on your foot. And because that ball starts moving forward, it means there's a force acting on it, and that's the force of your foot acting on the ball. The magnitudes are equal and the directions are opposite. Here's a very unfortunate application of Newton's laws. This car stopped. Okay, it's one way to describe what happened to the car. It stopped because of Newton's second and third law. So during the impact of the accident, the car exerted a forward force on the tree, which is evident by the tree, maybe being bent a little bit or scraped up. And in accordance with the third law, the tree exerted an equally strong force back on the car in the opposite direction. And that's what caused the crumpling of the front of the car. When you think about it in terms of the second law, right, which is the sum of all forces adds up to the mass times the acceleration, the force of the tree on the car gave the car an acceleration, a negative one, that changed its velocity to 0. Let's look at some conceptual examples that will illustrate some aspects of Newton's third law and train you on how to identify them, how to identify the force reaction pairs. So let's say your car breaks down and you start to push it to the nearest repair shop. While the car is beginning to move, how does the force you exert on the car compare to the force that the car exerts on you? And so kind of an auxiliary thing. How are you interpreting this statement? The car is starting to move. I want you to look at that and I want you to think that the car is accelerating. Right? It's starting to move. It's not moving at a constant speed yet. It's beginning to move. So its speed is variable and thus it's accelerating. And so what this first sentence or second sentence states is, while the car is accelerating, so while Newton's second law is active, how does the action-reaction force pair between the car and you compare? Well, the action-reaction force pair has nothing to do, right, with either Newton's first or second law. So Newton's third law is like independent of Newton's second law. So, in other words, the force that the car exerts on you is still going to be equal and opposite to the force that you exert on the car. Okay? The fact that one of the objects is accelerating doesn't play a role in how to apply an action-reaction pair. And then, so the second part is, how do these forces compare when you're pushing the car along a constant speed? And so when you think constant speed, I want you to think not accelerating. And therefore, the sum of all the forces is going to equal 0, which is Newton's first law. So your action-reaction pair does not care if either object is accelerating or not. It's independent. And so the forces are still going to be, the action-reaction pair between you and the car, still going to be equal and opposite. Okay? So let's practice, drawing all the forces on an object. And this is a great example to do that, as well as understand Newton's third law. So we have an apple sitting on a table. Let's draw our apple in our table, okay? And they're in equilibrium because they're at rest, they're not moving. What forces are acting on the apple? So I'm going to draw a free body diagram. Free body apple. Free body diagram of an apple, which is basically me, approximating the apple as a point particle and applying all the forces on that apple. And so the apple's sitting on the table, so there's definitely going to be a normal force acting on the apple due to the table. Table on apple. And then the apple weighs something. So we're going to have the weight of the apple. Mass of the apple times gravity. So what are the forces acting on the apple? Well, the ones we just described. The normal force of the table on the apple and the weight of the apple, which is the force of gravity or the force of Earth on the apple, right? There's nothing else going on with the apple. So what is the reaction force to each of the forces acting on the apple? So the normal force of the table on the apple, what is its action-reaction pair? Well, it's going to be the force of the apple on the table. It's the force of the apple pushing down on the table. So if we were to draw a free body diagram of the table, that action-reaction pair would be right here, right? It's the force of that heavy apple pushing down on the table. So I'll make these red. So what is the action-reaction pair of the weight of the apple, right? The weight of the apple is the force of Earth on the apple, right? That's what the weight of the apple is telling us, right? Earth is pulling the apple down. So the force of the Earth on the apple is down. What is the action-reaction pair of that? Well, that's going to be the force of the the apple on the Earth. And that's a funny one to think about. Like, what it is it's the apple pulling up on the Earth, okay? First of all, the apple has no arms, right? So that's an issue. And second of all, Earth is gigantic and an apple is little, so how could it possibly pull up on the Earth? Well, I mean, it's not moving the Earth, but the force is there. The force must be there because of Newton's third law. The force exists, right? Just because the force isn't producing an action doesn't mean that the force doesn't exist. Okay, we're getting like a little philosophical here. So, what we could do, so we got the action. Oh, what are the action-reaction pairs, right? That's basically what we just described. But if we look at the free body diagram of the table, it's not done. We didn't finish. We didn't mark. We marked, here's the weight of the apple, but we didn't mark the force of the apple on the Earth because in order to do that, we'd need to draw a free body diagram of the Earth, right? Because the thing about Newton's third law is those forces that are related to each other through Newton's third law do not all belong on the same object, right? One is describing the force on one object and the other is describing the force on the opposite object. So we would need to draw the free body diagram of Earth and draw a vector of it being pulled up by the apple, right? And so that would be this F apple on earth. We could fill in the rest of the free body diagram of the table. So like you would have the weight of the table, right? The heaviness of the table being pulled down by earth. And then you would also have the normal force of earth on table, which we didn't talk about here, right? These are not related to the action-reaction pairs of the apple, which was the original question, right? These are just additional forces that just to finish out the free body diagram. Okay, and then for the earth, we would have the table's force pulling up on that, right? Sun would be pulling on the earth in some other direction. This is a good practice identifying forces and how they're related to each other. So let's do it one more time. So we have, and this is going to be related to tension forces, which you'll have a lot of homework related to tension forces. So we have a stone mason, so this guy, and he's dragging a block with a rope, okay? The block is not necessarily in equilibrium, meaning the block could be accelerating. So the question is, what are the forces that correspond to the actions or the interactions between the block, the rope, and the mason? And what are the action-reaction pairs? So we're going to do it this way, the free body diagram of the block, and then we'll do the free body diagram of the rope, and then we'll do the free body diagram of the guy. Okay. And so what are all the forces acting on the block? So the block is, it's on the surface of the earth. So therefore it's got a normal force and a weight. And then there's a horizontal force, which is going to be equal to the force of the rope on the block. Okay, force of the rope on the block, which that has a name, which we call tension. So I'll mark that as like T1, the first tension. So what about the rope itself? The rope is going to feel, the rope is massless at this point, so we're going to ignore any mass of the rope, and we're going to write what the rope is feeling. The rope is feeling a tugging from both ends, right? It's feeling a tugging from the rock and a tugging from the man. So this would be the force of the block on the rope, and this would be the force of the mason, on the rope. These are also tension forces, right? They're pulling forces. So I'll call this T2 and I'll call this T3. And so what about the mason? What's he feeling? He's got a weight and a normal force, which we really don't care about in the context of this question, but I'm writing them just for practice. And so what's happening to the mason when he's pulling on the block? Well, the block and the rope are pulling back on him, right? So he's going to have the force, specifically the rope pulling on him, because he's not in direct contact with the block. So there's for F rope on mason. That's going to be the fourth tension. And so those are all the forces. So the forces that correspond to the interactions between those three parties is going to be these guys, the tensions, right? The normal and the weight are interaction forces between the ground and the earth. So we only care about the interaction between block, rope, mason. So the question is, what are the action-reaction pairs here? The action-reaction pairs are going to be these guys. So in other words, tension 1 is going to be equal to negative tension 2, and here tension 3 is going to be equal to negative tension 4. And you can see that because of how we labeled the forces, right? Force of rope on block, force of block on rope, which we called T1 and T2. So those are going to be action-reaction. Force of mason on rope, force of rope on mason. Okay? That was my chair, by the way. So now this is a question I get a lot, and that I'm sure it's just a common question from students. Is like, well, okay, if I'm pulling on something really hard and it's pulling back on me equally as hard, how can it ever accelerate? And so what this question is making a false assumption. And the false assumption is that these two forces here are going to be added together to, are going to be added together, which you do not do, right? You can only add up forces. You can only apply Newton's first or second law on a particular object, that one object of mass m. And if you read these two forces, the object pulling on you, that's the force on you. And then the object, you pulling on the object, well, that's the force of the object. So you would not add those two force vectors together because they do not belong to the same thing, right? They have different masses and different other forces acting on them. So you wouldn't add them together, okay? That's the difference between Newton's second and third laws. So Newton's second, or even Newton's first law, apply to a particular object. And then Newton's third laws relate the forces on two different objects. All right. So I've been talking a lot about free body diagrams. Haven't, been formally introduced yet, but here they're getting introduced. So free body diagrams are a technique of problem solving. And what you're doing essentially when you're constructing a free body diagram is you're labeling all the forces acting on one object. Okay, so only the forces acting on that object matter, and whether the object is moving or not, that's when you decide to apply first or second law. I shouldn't say moving, right? I should say accelerating. So we use free body diagrams to help identify the relevant forces. So here's a couple of pictures. So in this snapshot, the runner is about to take off, and they are in contact with the ground in one spot here on the foot. So what we're going to do is, even though the force between the foot and that launching pad occurs at the foot location, while maybe the mass, her center of mass is near her body, right? What I'm getting at is that we are going to reduce this woman down to one dot, okay? And we're gonna make the assumption that all the forces acting on her are acting at this one location. All right, and that's an important concept to make because that's where things can get a little bit, you're not able to properly visualize it in your head when you're doing problems, okay? You need to realize that we're condensing this poor lady down to a single dot. And all the forces acting on her are being acted on in that one particular dot. And so what are the forces acting on her? Well, we have her weight, right? Her weight vector pointing straight down. But then we have the normal force, right? And the normal force, you can see her foot is at an angle. So the normal force is not going to be exactly straight up. It's going to have a component kind of off to the side, right? Or it's going to have a vector off to the side, because we'll have an X and a Y component. So that's what we are examining here. And this is done purposely, right? This is going to help her launch and go faster, which is why you don't start from like a perfectly upright position. You're starting from a position at an angle. What about these two basketball players? One's in the air, one's touching the ground. Well, they're both going to have the weight vector, right? They're both going to feel the force of gravity no matter where they are, on the ground or flying. However, the only person that feels the normal force is going to be the one that is in contact with the floor, because the normal force is the floor pushing up on that person. So finally, we're eventually going to talk about some additional forces. All right, we haven't been introduced to buoyancy, thrust, or drag force yet. We'll learn about buoyancy in chapter 12. And then we'll discuss force of thrust and drag at the end of chapter 5. But if we're examining this situation, we have a scuba diver and they are moving, horizontally. And well, they're not in contact. Okay, let's start off with what we know. We know for a fact that they're experiencing a force of earth acting on them, pulling them down. So that's going to be the weight. But they're not in contact with the ground, right? They're in water. So they don't experience a normal force, but instead they experience buoyancy, right? A lifting force, the force of floating. So that's going to be pointing up. And then kicking their legs is creating a thrust, which is a forward moving, a forward pushing force, right? A thrust is moving you forward. So that is caused by the kicking of the legs. And then finally, when you're swimming in water, you feel a little bit of resistance to your motion. And so in fluids, we call this the drag. This is the force of drag. So these are just some forces, common forces acting on objects. So that wraps up chapter 4. Chapter 5, we're going to be applying Newton's laws to a variety of situations. And we're going to basically be doing a lot of examples, which is why I am going to offer you this recording of a lecture versus sitting in lecture. Well, you'll have time to speed it up, slow it down wherever you need to. So we're going to be applying Newton's laws. Let's have a little reminder. Newton's first law. We use Newton's first law when objects are in equilibrium. And so when an object is in equilibrium, that means it's not accelerating. And if it's not accelerating, that means it's either at rest or moving with constant velocity. And so if something is in equilibrium, all the forces acting on it are going to equal 0. So here's some problem-solving strategies. So if you get stuck on a problem, follow these directions. So let's do some examples together, and we're going to start off real easy and really work on labeling our free body diagrams. So we have a gymnast with a mass of 50 grams suspending herself from the lower end of a hanging rope. And the rope is of negligible mass, so we're going to ignore the mass of the rope and thus the weight of the rope. The upper end of the rope is attached to the gymnast. It's attached to the ceiling. And the question is, what is the gymnast's weight? Well, we don't need to draw a free body diagram in order to find the gymnast's weight. The weight is simply equal to the mass of the gymnast times gravity. And that is 490 newtons. Part B, what force does the rope exert on her? So the subject is her, and what we'll do is we're going to draw a free body diagram of her. And so she is a dot. And so let's think about all the forces acting on her. So, well, the earth is pulling on her, right? So she's going to have a weight equal to mg. What else is pulling on her? The rope, right? She's in contact with the rope. And so the rope, this is going to be the force of the rope on her. And that's all the forces acting on her. And so in order to solve for the force of the rope on her, which is what we were asked, we need to apply Newton's first law, add up all the forces in the y, F, rope, her, oh goodness, rope on her, on gymnast, okay, and we're going to subtract the weight and set that equal to 0. And we're subtracting the weight because that vector is pointing down. And so now, obviously, the force of the rope on the gymnast is going to be equal to 490, right? That's the weight of the gymnast. And the direction of that is up. What is the tension at the top of the rope? So we're looking for the tension at the top of the rope, which means we care about the rope and what it's feeling. So we're going to draw a free body diagram of the rope, and that's obviously just a dot. So what are all the forces acting on that poor rope? Well, the gymnast is pulling down on the rope, right? But the ceiling is also pulling on the rope as well. And because the rope is massless, we're going to ignore any weight due to the rope. So the question is, what is the tension at the top of the rope? That's going to be equal to the force of the ceiling on the rope. And if we add up the forces and set them equal to 0, we are going to see that T, the tension, equals the gymnast, force of the gymnast on the rope. And what is that? We already found out what the action-reaction pair was, right? The force of the rope on the gymnast was 490. So we know the magnitude of the tension is going to be also 490. And the direction is up. Let's add some mass to the rope and see how that changes. And I want you to pay attention to the procedure that we're doing here, okay? So we need to find the tension at each end of the rope in that example if the weight of the rope is now included, and it's 120 newtons. So what we need to do is we need to draw a free body diagram for the rope and the gymnast like we did before. But now the free body diagram for the rope is going to have an additional vector. I'm going to erase this one for now because this is just what we're going to get to that. Okay, so we're going to draw the free body diagram for the gymnast. I'm not going to redraw it. We had this force of the rope on the gymnast, which is the tension. And then we have the gymnast's weight, right? So that's the free body diagram for the gymnast. Now let's do that for the rope. So remember we had the force of the ceiling on the rope and the force of the gymnast on the rope, but now we have an additional vector because we're not ignoring the weight of the rope. We now have weight, and so we're going to have an additional vector of the heaviness of the rope, right? The force of gravity pulling on the rope, pulling it down. So now let's apply Newton's laws to part A. So let's do Newton's first law. On A, figure A. And so we have sum of all the forces is going to equal TRG minus WG, which equals 0. And we knew what WG was. WG was 490, right? So what we found is that TRG is simply equal to 490 newtons. Now we are looking to solve, like what is the question asking us to solve? It's asking us to solve for these two, right? The tension at the top and the bottom of the rope, at each end of the rope. So it's asking for tension force, which is the force of the ceiling on the rope, and the tension force, which pointing down, which is the force of the gymnast on the rope. So we need to solve for those two. So let's apply Newton's laws to free body diagram B, and it's going to be Newton's first law since it's not moving. So sum of all the forces is now going to be equal to positive TCR minus TGR minus weight of the rope, and all that's going to equal 0. So we have two unknowns, right? Because we know the weight of the rope. Which is 120 newtons. So we have two unknowns. Okay. Oops, I meant to highlight those. Right. We have two unknowns. Is there any information that we have that we could use to get rid of one of the unknowns? And the answer is yes. We have the action-reaction pair between rope on girl, or rope on gymnast, and gymnast on rope, which appears right here. So we know that the magnitude of TRG is going to equal the magnitude of TGR. So now we can plug that in. And we can solve for TCR, which is 610 newtons. So the tension at the top of the rope, which is TCR, is going to be 610 newtons. And then the tension at the bottom of the rope, which is TGR, we saw was equal to 490 newtons. Okay? So that is how you use Newton's laws, right? You are going to start off with first or second law, and then possibly you need to invoke the third in order to eliminate some unknowns. All right, that's the big picture idea. So let's do some examples where we are practicing complicated vector decomposition and addition. Okay, and this is such an example here. So we have a car engine hanging from a chain, and it's linked with an O-ring, and then two ends of the chain are attached to corners of or sides of a wall. And so what we want to do is find the expression for tension in each of the three chains in terms of the weight. Okay, so we're going to solve for T1 in terms of weight. We're going to solve for T2 in terms of weight. We're going to solve for T3 in terms of weight of the car engine. And we're going to ignore the weights of the ring and the chains. So what is the object that is mediating all these tensions? Right? All these tensions are connected to the ring. So what we could do is we could draw the free body diagram of the ring. And an object doesn't need to have a mass in order for you to draw a free body diagram on it. Okay? All it means if it doesn't have a mass is that there is no force due to gravity that we're going to consider. So let's draw it. So we have our tension 2 coming to the left, and then we have tension 3, which is at an angle, okay, where this angle is defined. And then finally we have the tension force pointing straight down. And so using this free body diagram of the ring, we can add up all the forces, and we know that the ring is not moving. So all the forces in the X and all the forces in the Y should add up to 0. So let's do that carefully. So let's add up all the forces in the X first. So T1, there is no X component. T2 has an X component, and it's negative. We don't know the magnitude, so we're just going to keep it as T2. And then T3 is going to have an X component, and it's going to be positive. And so what we need is to figure out what that value is. We were told that this angle up here is 60 degrees. So that would make this angle here also 60 degrees. And it makes it a lot easier to apply your triangle in that way. T3x is going to be the magnitude of T3 cosine of 60. And then let's add up all the forces in the Y. So we have a negative T1, and then we have a positive T3 sine 60. And now we get to the point where we have 2 equations and 3 unknowns. So we need to invoke another law in order to make this a solvable series of equations. Okay, right? We need a value for something, because you can solve 2 equations, 2 unknowns, but you can't solve 2 equations with 3 unknowns. So let's draw a free body diagram of the engine. Okay, so the engine has got some weight, W, which is the force of the earth pulling on the engine. The only other thing the engine is in contact with is that ring with the tension in the first chain, T1, right? There's nothing else touching the engine. So we can apply Newton's first law to this situation, and we see that all the forces in the Y are going to add to 0. And so since W is a known, we know that T1 is going to equal W. And now we can plug that into our previous Newton's first law equations that we built for the ring and eliminate an unknown. So I'm going to label these equations 1, 2, and 3. And so I'm going to take 3 and insert into 2. So I'm going to get 0 equals negative weight plus T3 sine 60. So now I can solve for T3. I'm just leaving it as sine 60. I'm not evaluating it. We're just going to, move it around like a variable. So we've solved for T3, and we know T1. So now all we need to do is find T2. So now that we know this is T3, we can insert T3 into equation 1. So equation 1 states that negative 0 equals negative T2 plus T3 cosine 60. And we know that T3 equals omega over sine 60. So now we substitute and we see that T2 is going to equal omega cosine, it's OW. Suddenly I'm speaking Greek. Sine 60. So now we have all three tensions in terms of W. T2, T3, T1. So do you see the procedure, right? I'm treating these problems as if I am building equations that I can use to solve for one another, right? Building a system of equations. And I'll need to invoke Newton's first or second on multiple objects, or I'll need to invoke Newton's third in order to relate two forces between two objects. So that is the big idea here. All right, the good old inclined plane. So inclined plane problems, we're going to be kind of tilting our coordinate system. So you'll see what I mean. So we have a car and it's on a ramp, slanted ramp, which is slanted by an angle alpha from the horizontal. So only a cable running from the trailer to the car prevents the car from rolling off the ramp. Find the tension in the cable and the force that the ramp exerts on the car's tires. So they've already drawn the free body diagram here, and they've drawn it on the car. So what are we looking for? So we have our forces identified. Let's see if any of those forces are the ones that are asked about in the question. Find the tension in the cable. Okay, so we're solving for T. And the force that the ramp exerts on the car's tires. So the force that the ramp exerts on the car's tires, that would be the normal force, right? The normal force is the force of the surface exerting onto you. And so the tires are in contact with the surface of the ramp, so the normal force will be the force of the ramp on the tires. So we're going to apply Newton's, so nothing's moving, right? So we're going to apply Newton's first law in the X and the Y. So let's uncover all the forces in the X, but hold on, we need to figure out what our coordinate system is going to be. And so whenever you have an inclined plane problem, what you're going to do is you're going to tilt your coordinate system so that the surface is parallel with the x direction. And so maybe we should redraw everything just so that we can put our coordinate system on top and clearly see, right? So this is our x and our y, okay? So now let's find out the forces in the x. Well, first of all, the tension is going to be in the x, and it's pointing to the right, so we're going to have a positive tension. And then we have something else that has an x component, and this is going to be the weight vector. So the weight vector is going to have a negative y component and a negative x component. And we need to figure out what those are and how they relate to this angle right here. So what I'll do is I'll draw the ramp. Okay, there's the ramp, and here's angle alpha. And then I'm going to draw the weight vector on top of that. And so the weight vector, if you look up here at the picture, the weight vector acts as the opposite side of the black triangle. So that's going to be the magnitude of the hypotenuse of that triangle. And the x component is parallel to the ramp up there, right? And then the y component is perpendicular to that. So here's our right triangle. This is going to be the y, and this is going to be the x. And so if you look at this, you can see that this angle right here must be 90 minus alpha. And because these are perpendicular, this angle right here must be alpha. So to compose our components of the weight vectors, we now have alpha defined. So the x component is going to equal the magnitude times sine alpha. And then the y component is going to be magnitude cosine alpha. So you can see that the x and the y's are switched. And that's because alpha is being defined with respect to the y-axis and not the x-axis. And so now when we put these into our coordinate system, right, at this moment I'm treating it like a triangle. Okay, this is in triangle land, triangle universe. When I put them into my coordinate system where I'm adding components, I need to put negative signs in front of those x and y components, right? Because they are pointing down on my coordinate system and pointing to the left. So now I have my x component, which I know is negative, and it's equal to negative omega, I said omega again, sine alpha. That's w, little w. And do I have anything else in the x direction? No, I do not. So now let's add up all the forces in the y. And what I have in the y is I have the normal force pointing up in the positive y direction. And then I have my y component of my weight vector, which is going to be cosine alpha with a minus sign because it's pointing down. And so now let's go back and see what we need to find. We need to find tension. So we need to solve for tension. And if we solve for tension, we can solve it straight from, I'll call this equation 1 and equation 2. Tension is simply equal to W sine alpha. And those are givens in the problem, right? This is a given in the problem. And alpha is technically a given in the problem because it's in the image, okay? So we have fully expressed tension. And what you can see from here is tension is the y component is equal to the x component of the weight. So now the next thing we need to solve for is N, the normal force, which is the force that the ramp exerts on the car's tires. So we'll use equation 2 to solve for N, since W and alpha are knowns, and you're going to see that normal force is the y component of the weight, is equal to the y component of the weight. Okay? So this is how you'll treat inclined plane problems. And there may be more forces involved, right, depending on the situation. But this is the general idea of how you treat an inclined plane problem. So let's take a look at example 5.5, where we have the inclined plane and we have some additional forces. We have the force of tension, which is caused by a hanging bucket full of, rocks or something. Okay. So what we need to do is we need to haul granite blocks up a 15-degree slope, and lower, doing that will lower the bucket that has some granite in it. Okay. And so the question is, how must we relate the weight of the cart to the weight of the granite in the bucket in order for the system to move with constant speed? So what we're going to do is we're going to apply Newton's first law, right? Constant speed. Newton's first law to both the cart and the bucket. So let's start off by drawing a free body diagram of both objects. So the free body diagram of the cart can be represented by a dot. And the dot is on an incline. So what I'm going to do is I'm going to kind of sketch my x and my y axis. And so I'm going to have a normal force, which is 90 degrees from the surface. And then I'm going to have a weight vector, which points straight down. And then I'm going to have tension due to the cable that's connecting the cart and the bucket. And there's no other forces acting on the cart. Let's draw the free body diagram of the bucket. So the bucket is on a level, we don't have to rotate our coordinate system here. So we can have a coordinate system that is straight up and down, usual business. Bucket is going to feel its own weight, right? Weight 1 and weight 2. And it's going to feel tension due to the rope connecting the cart and the bucket. So now we're at a point where we can apply Newton's first law, which is going to ensure that we are relating these quantities to the fact that they are moving with no acceleration. So let's apply Newton's first law. So we're going to add up all the forces in the x and set it equal to 0. And so let's identify all the forces in the x. We have a positive tension and we have a negative weight in the x, right? And we can go ahead and figure out what that is. So if the ramp itself is 15 degrees, well then this angle right here will be 15 degrees. And so we will get the weight times sine of 15 degrees. That we'll call equation 1. Equation 2 will be the sum of all the forces in the y. And the sum of all the forces in the y on the cart will be the normal force pointing up minus the component of the weight in the y direction. And that is going to be W1 cosine 15 degrees. Now let's apply Newton's first law to the bucket, and all of it is all of the action of the bucket is along the y direction. So we're going to add up all the forces in the y, set it equal to 0, and that will equal the tension minus the weight. So the question is, we need to relate, how should W1 and W2 be related? So what we could do is we could solve for W1 and solve for W2 and take a look at how those two functions are related to each other. So weight 1 We can solve for that over here. If we find that the tension, right, we solve for the tension in equation 1 is equal to weight 1 sine 15. The normal force is equal to weight 1 cosine 15. And here we see in equation 3 that the tension is also equal to weight 2. So by combining equation 1 and 3, we can come up with a relationship between W1 and W2. So if the ratio of the two weights is equal to sine of the angle of the ramp, then we can ensure that the system will move with no acceleration and thus constant speed. So we've done several examples where the object was either not moving or moving with constant velocity, and we applied Newton's first law. Now we'll look at some examples where we're going to apply Newton's second law. These objects are not in equilibrium and thus they're accelerating, so we'll set the right-hand side this time equal to the mass of that particular object times its acceleration. So one common mistake, common error is to include the right-hand side of Newton's second law on the free body diagram. And that does not belong on the free body diagram because why? Because it's a result of the addition of the forces that are acting on the object, right? So if we add up all the forces acting on an object and it's accelerating, it would be equal to the mass of that object times the acceleration. This is what belongs on the free body diagram. The right-hand side of Newton's second law does not. This is a result. The result of all the force vectors you do not put on the free body diagram. How you would interpret the right-hand side of Newton's second law on your free body diagram is you could draw the direction of the net acceleration. And so that would just be a floating vector that illustrates to you what direction the object is accelerating in. We do not include MA on the free body diagram. So this is a little problem-solving strategy for doing dynamics problems, so you can refer back to that when you're working on your own. So let's do this example here. So we have a boat and it's moving on a frictionless horizontal surface. And due to the blowing wind, 4 seconds after the ice boat is released, it's moving to the right at 6 meters per second. The question is, what horizontal force, constant horizontal force, does the wind exert on the ice boat? And the combined mass of the ice boat and the rider is 200 kilograms. So we're concerned with the ice boat, and we're gonna draw a free body diagram of the ice boat. And we know the ice boat has some weight equal to 200 kilograms times gravity. So we can go ahead and figure out what that is. 1960 newtons. And it's sitting on the surface of a pond, so there's going to be a normal force. And then, so what's going on in the horizontal direction? So the wind is blowing, so there's going to be a thrust force on the ice boat, moving it in the direction of motion. So that's going to be our FW, right? That's the force of the wind. That's the thrust of the wind exerted on the ice boat. And the ice boat is moving to the right. So the question is, what is the value of that FW? What is it? So we know that the boat is moving to the right. And we're given some terms here that we need to recognize. The force is constant. So the horizontal force is constant. And so what that's going to tell you is that if the force is constant, the acceleration must be constant. And so we can open up kinematics with constant acceleration into this problem. So sum of all the forces acting in the x direction, all we have is that force due to the wind, and Newton's second law tells us that that's going to be equal to the mass of the object times the acceleration of the object. So we're finding FW, we know M, and we don't know anything about the acceleration, but we are given actually some information. We know that it's initially at rest, and after 4 seconds, it's moving to the right at 6 meters per second. We can use that to determine the acceleration. And we're going to use equation 1, where the velocity at any time t is equal to the initial velocity plus acceleration times time. So we know 6 meters per second is the velocity. Initial velocity 0, a is what we're solving for, and time of 4 seconds to get to that new velocity. And so the average acceleration then is going to be 6 meters per second over 4 seconds, which is, let's do 3/2 meters per second squared, 1.5. So now that we know that, we can use that to solve for our unknown, which is the force of the wind. So now that we know that, we can use it to determine the force of the wind. So we're going to take this acceleration and insert it into here and solve for FW. The force of the wind must be 300 newtons. Second question. And that completes this example. Let's modify the previous example by including now the force of friction. So we're including the force of friction, and now our free body diagram is going to change slightly. We're going to have the addition of a new force. So we can redraw the free body diagram of the boat. We have our weight, we have our normal, we have the wind force, and now we have a frictional force which is going to oppose the motion direction. The value of that frictional force is 100 newtons. Now, what is the constant wind force required to keep the same acceleration of 1.5 meters per second squared? Add up all the forces in the x, and that should equal the mass of the boat times its acceleration of 1.5. When we add up those forces, we have the wind force minus the frictional force. So we plug in everything we know, solving for the new wind force, and we're going to get 300 newtons plus 100 newtons is going to equal our new wind force that must be required. So the wind must push an extra 100 newtons more in order to compensate for the frictional force, which I think makes complete sense when you say it like that. And now you see how the math supports that. So let's talk about elevators. Elevator problems are fun. They really test your conceptual knowledge of what it means to accelerate and decelerate and the signs of those accelerations. So imagine you're an ISA and you're in the elevator, and you in the elevator weigh 800 kilograms. The elevator is initially moving downward at 10 meters per second, and it slows down to a stop. During that slowdown, it's feeling a constant acceleration. And that distance of the slowdown is 25 meters. The question is, what is the tension in the cable while the elevator is being brought to rest? So the elevator is in motion and it's accelerating. So what we need to do is we need to apply Newton's second law to this elevator. Let's draw a free body diagram of the elevator. So the elevator and you weigh 800 kilograms. So that's going to be the weight. And you're not on the ground, right? The elevator and you are not resting on the ground yet. We're in the process of going down, but we are being held by a cable. And so there's going to be a tension in that cable pointing up. Now, what is the direction of our acceleration? We are moving down, but we are moving down with decreasing speed. So that means that we must be accelerating upward. That is the most difficult conceptual part of this whole problem. That means we're accelerating upward. And so we need to identify that, because when we build Newton's second law, we need to know what sign the right-hand side should be, right? This is going to tell us the sign of the right-hand side. So the left-hand side, sum of all forces in the y, we're going to have the tension minus the weight, and that's going to be equal to the mass of the elevator times the acceleration of the elevator. And that's going to be positive. And so we're solving for the tension in the cable. We're solving for tension. So we know that tension is going to equal ma plus the weight of the elevator. So in order to find tension, we need to know the mass, we need to know the acceleration, and we need to know the weight. We know two of the three. So we can use some kinematic information to find the acceleration of the elevator. So the elevator, let's see what we're given. We're given initial velocity. We're given the distance of the slowdown, the distance of the acceleration. Distance that we decelerate is 25 meters. So that means we are starting from 25 and going to 0. And so our delta y in this case is going to be negative, because it's final minus initial, 0 minus 25. Our final velocity when we reach 0 meters is going to be 0 meters per second, right? We want to be completely stopped by the time we hit the bottom of the shaft. So now we can use that to solve for A. We're going to use equation 3 of the kinematic equations. So we're going to get 0 equals 100 meters squared per second squared. I'm already doing the math. Plus 2a times negative 25 meters. And we're going to get positive 2, right? This is 2 times 25. 100 divided by 50. So we're going to get 2 meters per second squared as our acceleration. We can take that acceleration and plug it back into our original equation for tension. Oh, just kidding. 800 kilograms. I'm like, why am I writing 200? So our tension is going to be equal to 9,440 newtons. Let's do another elevator example. We have a woman standing in the elevator and she's on a scale. The elevator is moving downward with decreasing speed. What is the reading on the scale? So this is an interesting example because we can see how our weight might change depending on whether or not we're accelerating or decelerating. We'll also learn about what it means to read your weight on a scale. Concerned with the reading on the scale. So let's start off a little strangely by drawing a free body diagram of the scale. So let's think about everything that the scale is feeling. The scale is feeling a force downward due to the weight of the woman, right? So we'll call this the force of the woman on the scale. And we're going to ignore the weight of the scale. The scale is also sitting on the surface of the elevator, so it's going to feel a normal force due to the elevator on scale. So we're taking this route because we're going to need to describe the reading on the scale. And the reading on the scale is a result of the Newton's action-reaction pair between the force of the woman on the scale and the force of the scale on the woman. So now let's draw our free body diagram of the woman. So the woman weighs some amount mg, and she's going to feel a normal force of the scale, so the force of the scale on the woman. And they're moving downward with decreasing speed, which means they are experiencing an upward acceleration. So now that we know how to relate the force of the scale on the woman to what the scale actually reads, we know that we just need to solve for this quantity here. So let's apply Newton's second law to this situation. Sum of all the forces in the y, we're going to have the force of the scale on the woman, which is what we're solving for, subtracting the woman's weight since that vector is pointing down, and all that should equal the mass of the woman times the acceleration that she's feeling. So all we need to do is determine the acceleration of the woman. The acceleration of the woman is going to be the same as what was given in the previous example, right? We saw that the acceleration of the elevator, and thus the woman, was 2 meters per second upward. 2 meters per second squared upward. So the scale reading, which is the force of the scale on the woman, action-reaction pair, is simply going to be equal to 50 kilograms times 2 meters per second squared plus her own weight. And it's going to be equal to 590 newtons, right? Which is greater than what she would read on the scale if she just stepped on it while not accelerating. So she feels heavier, right? The scale is reading a heavier value because the elevator is decelerating and thus producing a positive acceleration upward. There is a great analogy to this example, and it has to do with your apparent weightlessness due to your own acceleration. For example, what we just saw was that when a passenger rides in an elevator with some y acceleration, the passenger's apparent weight changes, and it increases or decreases depending on the sign of the acceleration. So the passenger's apparent weight, which is equal to the normal force that the surface exerts on the passenger, is going to increase for positive AY, and it will decrease if your acceleration is pointing down. There is an extreme case that occurs when the elevator has a downward acceleration of g, negative g. That is when the elevator is in free fall. And in that case, the normal force acting on the passenger is effectively 0, and the passenger seems to be weightless. This is what happens when satellites or even astronauts orbiting the Earth, they have moments of experiencing apparent weightlessness because they are essentially in free fall heading towards the Earth and thus are floating in space. So let's do this example where we deal with an inclined plane, and we are going to examine how the acceleration of these students in a toboggan is affected by the forces acting on them on this inclined plane. Specifically, we'll find the acceleration. So we'll start off with our free body diagram, and since we're dealing with a ramp, we're going to make our x direction along the ramp and our y perpendicular to that. And so now we're going to draw the forces. Weight vector pointing down, normal force pointing perpendicular to the surface. And those are the only two forces acting on the toboggan and the riders. So if we wanted to find the acceleration, we would need to add up all the forces acting on the riders in the x and in the y, and set it equal to mass times acceleration. So if we take a look at the way we set up this problem, the riders are sliding down the ramp, and the ramp is the x-axis. So they will not be accelerating in the y direction. So that is actually going to be equal to 0. And so in order to find the acceleration, all of the acceleration is along the x direction. So what forces are pointed along the x direction? Well, we have a component of the weight in the x, and then there's also one in the y. And so this is that triangle formed by the ramp, and the angle of the ramp, alpha, is right here, which would make this angle 90 minus alpha. And so if that angle is 90 minus alpha, you're essentially going to flip the sine and the cosine. So when we write the x component, we're going to have a positive w, and it's going to be cosine of 90 minus alpha, which ends up being sine, right? So I'm going to rewrite it as weight sine alpha. Is there anything else in the x direction? No, there is not. So now let's, just for the sake of the problem, let's add up all the forces in the y. So we have n pointing up, and then subtracting wy. What is wy? It's going to be w cosine alpha. And that's going to equal 0. So what we need for this problem is we only need to find the acceleration. And so we really only care about this. So to find the acceleration, I'm going to solve. And we see that the acceleration of the students in the toboggan is determined by their mass, collective mass, and also the component of the weight along the x direction. And so since we weren't given any values, we are just expressing this acceleration in terms of the givens, which are the mass, the weight, and the angle of the incline. So this is simply a symbolic exercise to illustrate this concept. The concept is that what's causing these you to slide down an incline is gravity. It's the force of gravity that is along the component of it that's along the ramp's direction. So let's take a look at this example. We have a food tray and we're pushing it with a constant force of 9 newtons. The tray has a milk carton on it, and the tray and the carton are sliding on a greasy surface so that we can ignore friction. Find the acceleration of the tray and the carton and the horizontal force that the tray exerts on the carton. So we're going to be drawing 2 free body diagrams, one for the tray, one for the carton. So the tray is feeling a push, right? A push of 9 newtons. And according to this picture, it looks like it's being pushed to the left. So the force of the push will be pointing to the left. And what else is that tray feeling? It's going to feel the force of gravity due to its own weight. And then it's going to feel a normal force. There is one more force acting on the tray, and that is the contact force between the carton and the tray. So the carton is going to be pushing on the tray to the right. So now, if we want to find the acceleration of the tray, we're going to need to add up all the forces in the x. Set that equal to the mass of the tray times its acceleration. Well, we know the force of the push is 9 newtons. We don't know the force of the carton on the tray. We know the mass of the tray, solving for acceleration. So we have one equation, 2 unknowns, so it's not solvable at the moment. Let's take a look at the free body diagram of the carton and see if there is any help there. So the carton is going to feel the weight of gravity. It's going to feel the normal force. And it's going to feel the force of the push, or I should say the force of the tray on the carton. Right? It's not feeling the force of the push exactly, because the push is not being acted on the carton. It's being acted on the gold tray. So what the carton feels is the force of the tray pushing on the carton. And those are all the forces acting on the carton. So now using that free body diagram, let's construct some equations. So the sum of all the forces in the x direction are simply the tray's force on the carton, and that's equal to the mass of the carton times its acceleration. So we don't know this force. We know the mass of the carton, and we don't know the acceleration. But is there something that we know about how these accelerations are going to compare? So these accelerations are going to be equal because these two objects are connected together. And so when the hand pushes the tray, it's going to push the carton at the same speed. They're going to accelerate together. So we know that these are equal to each other. So we know that these A's are equal to each other, which would allow us to eliminate a variable. But we want to solve for A, so maybe we don't want to do that. What else do we know? We know that we have a Newton's third law pair between the carton and the tray and the carton. So these magnitudes will be equal. So what we could do is we could solve for F tray carton and insert that into this equation here, since the magnitudes are equal. So I'm going to make that substitution. I can go ahead and put what the mass of the carton was. And now you can see we have eliminated the unknown and we can now solve for A. So the concept here is that when you have two objects that are in contact with each other and there is nothing in between them that would, be like a stretchy cord or a spring or anything that's going to change their relative distance, then you can say that they will be accelerating at the same rate. And that allowed us to eliminate an unknown and solve for the acceleration. And we also used Newton's third law to eliminate the unknown. And so we have 6 meters per second squared as the acceleration. So we found the acceleration of the tray and the carton. They're both 6 meters per second squared. And now, can we solve for the horizontal force that the tray exerts on the carton? So now we're solving for F tray cart. So let's solve for F tray cart. Now that we know the acceleration is 6 meters per second. F tray cart is going to be equal to the mass of the carton times the acceleration, which is 3 meters per second. Just kidding, 3 newtons. Kilogram meters per second squared, 3 newtons. Okay? So this is a great example. So this example is one that you would want to fully understand in order to interpret problems that maybe you saw in the pre-lecture where you have boxes A, B, and C all being pulled, by one common force. Okay, this is going to be very similar arrangement to that type of problem. So now let's do some pulley problems. Two objects moving with the same magnitude of the acceleration. So we have an air track glider with mass M and it's moving on a frictionless air track. The glider is connected to a weight of mass M2. And then the string is light, flexible, non-stretching, which means that we're going to ignore any mass due to the string. And the non-stretching part is indicating that the distance between M1 and M2 is going to remain constant. And therefore, the acceleration of each object is going to be equal. Okay, so that's what the non-stretching part tells you. So let's draw what we need to do is find the acceleration of those objects and then the tension in the string. So we're going to break it down just like we did in the previous example. We're going to draw the free body diagram of both objects. This is the glider. And then this is the free body diagram of the mass. Oops. So let's look at the glider. The glider has a weight, it has a normal force, and it has the tension in the string pulling it. And which direction is the mass accelerating? It's accelerating to the right. I'm sorry, the glider. Now let's look at the mass. The mass has its weight, and it has tension in the string, and it's accelerating downward. So now let's construct the Newton's second law for each object. in the relevant direction, the direction of its acceleration. So we're going to do Newton's second law in the in the x direction for the glider. So we're just simply going to have the tension, that's the only force in the x, and that's going to equal to the mass of the glider, which is m1, times its acceleration. So now let's apply Newton's second law to the mass in the y direction. So we're going to add up all the forces in the y, and so if we decide to make upward positive, then the tension would be positive, the weight would be negative, and then the mass times the acceleration. So now look at the acceleration direction. It's pointing down. So that would need to be in negative acceleration here. We need to include that negative sign. And that's because what is on the right-hand side over here is the direction of the resulting force, which is the acceleration direction. And so since that's downward, we need to incorporate the negative sign on the right-hand side. So now we are going to solve for acceleration. So we need to eliminate an unknown. The unknown we need to eliminate is tension. So I'm going to solve for tension and insert it into the other equation. So here I'm going to get M1A minus, this is W2, okay, which is M2G equals negative M2A, right? This is M2. This is the mass of the mass. So now I'm going to solve for the acceleration. I'm going to combine my terms, move everything over. And you can see that the acceleration of those objects is going to depend on the ratio of the masses, okay? It's going to depend on the ratio of M2 with respect to the sum. And to determine what the tension is, tension in the string, well, we can take the knowledge of the acceleration and plug that into equation 1 here. So we can take A and plug it into equation 1 to solve for the tension, which is M1 times this big guy. And so the tension in the string is equal to M1 M2G over M1 plus M2. So in general, the acceleration is going to be less than G, right? In general, the acceleration is going to be less than G because this is going to be some number less than 1. This is a great example to do. Follow the video. So now let's spend some time talking about frictional forces in detail. So there's frictional force in this picture between the feet of the caterpillar and the surface in which it walks, and that allows it to walk up the walls, right? Same as a lizard that's walking up the walls. There's friction there that is allowing them to defy gravity. It's holding them in place. So let's take a look at the friction force in a typical situation of a box sliding on the ground. So we draw a free body diagram. We have the normal force, we have the weight force, and then the force of the push or the pull moving the box. And then if there's a friction on the surface, you're going to have a frictional force pointing in the opposite direction of the motion. And so the frictional force can be combined with the normal force into what's called the contact force, right? Because these are both forces due to the result of contact with the surface. One is simply due to the surface pushing up on the box, and the other one is due to the resistant nature of the box's surface against the surface of the table. And so we can combine those two into the contact force. So what is this resistance to motion that is coming from the table and the box's surfaces. Friction between two surfaces arises from interactions between the molecules on the surface. These molecules are exerting forces of attraction and repulsion, which slows down the speed of the block. You can imagine it as two rough surfaces encountering each other, and those bumps are going to slow down the motion. So we can define two types of friction. We have kinetic friction, which acts when the object is in motion, and the kinetic friction is given by a coefficient times the normal force. The static friction acts when there is no relative motion between objects. And the static frictional force, it can be less than or equal to another coefficient times the normal force. And so I want you to pay careful attention to this inequality here. And what this inequality is telling you is that the static frictional force is variable. All right? It's not a constant value like the kinetic friction. So let's talk chronologically about the forces that are acting on a box that is experiencing friction as we begin to pull on the box with a string. In general, before the box slides, static friction is going to act on the box, which we saw is a variable quantity. Then once the box starts moving, we'll have kinetic friction. So let's start at the beginning. At the beginning, we're not tugging on the box at all. And so if we draw a free body diagram, all that's going to be present is the normal force and the weight of the box. Now let's start tugging on the box very, very lightly, such that it's not moving. So when we tug on the box very lightly, such that it's not moving, you're going to have, of course, your normal and your weight forces. You're going to have the force of tension, but then you're going to have static frictional force. And let's say we wanted to determine what the value of that static frictional force is. Well, since it's not moving, you would use Newton's first law. And you would add up all the forces in the x. So you would get positive tension, negative static frictional force, and that's going to equal to 0. So the value of the static frictional force is going to equal the tension. And that's going to be true until the box starts moving. And so that's how you can see how the static frictional force is variable, right? It's going to depend on whatever tension is applied. And if that tension value is not enough to make it move, that is going to be the value of the static frictional force. At the moment the box is about to slide, we're going to reach the maximum static frictional force. And so as the tension gets bigger, we're going to approach that value. And so the maximum possible value for the static frictional force is the maximum tension we apply before motion. Here in picture 4, we have pulled with enough tension to cause motion. And so now when we draw the free body diagram, we're going to have the force of kinetic friction pointing to the left, which has a constant value equal to the kinetic friction coefficient times the normal force. Here is a graph of the frictional force as a function of tension applied to the rope. So as you can see, the static frictional force is going to increase linearly with tension. And so how do we know that? Because we know that the tension is equal to the static frictional force, which is equal to mu s times the normal force. And so as the tension increases, the static frictional force is going to increase proportionally. Something interesting happens, and that's the purpose of this graph, is the transition between static frictional force and kinetic frictional force. So the moment that you apply enough tension to cause motion of the box, the actual value of the frictional force is going to drop slightly. And then you're going to start tugging on the box at a smaller value than what you needed to do to start motion. And that's going to be constant no matter how much tension you apply. The frictional force due to kinetic friction is going to remain constant no matter how much more tension you apply. These are some values of coefficients of static and kinetic friction for different material combinations. And so you can see you have slightly different coefficients for static and kinetic friction. And you can see that static is higher than kinetic friction for most cases. When you get to really small coefficients, that breaks down. But for most cases, static is greater than kinetic. And that's exactly what this graph is telling you, right? The maximum static coefficient, which is mu s n, is greater than the kinetic friction coefficient because n is obviously the same. So let's check out this example of determining friction in horizontal motion. So we have a 500 Newton crate. We want to push it along a level floor, and we notice that to begin the crate's motion, we must pull with a force of 230 newtons. Once the crate starts to move, you can keep it moving at a constant velocity with only 200 newtons. So from that information, can we find the static and kinetic friction coefficients? So let's draw the free body diagram in situation 1. So in situation 1, we have the normal force and the weight, and then we have this push force or pull force of 230 newtons. And then we have our static friction coefficient because we are not in motion yet. Since we're not in motion, sum of all the forces in the x will equal 0, right? Newton's first law. And so we're going to have a positive 230 newtons subtracted by Fs. And so the static friction coefficient is going to be related to the static frictional force of 230 newtons, as long as we know the normal. And we know the normal force because in our head, we can apply Newton's first law to the y, and we see that the normal force is going to equal the weight. And so the static friction coefficient we can find because we know that the normal force is equal to 500 newtons. And so mu s will be 230 over 500, which is 0.46. So now that we are in motion, only a force of 200 newtons is required to keep it moving with constant velocity. Friction, kinetic friction will oppose that. And so we can use Newton's first law again, right, because of constant velocity, to find Fk. So Fk is going to simply be equal to F, which is equal to 200 newtons. And we know that that is equal to the kinetic friction coefficient times the normal force of the box. And thus mu K is going to equal 200 newtons over 500 newtons, which is going to be a fraction smaller than 0.46, which is what we expect, 0.4. Okay? So we are still following the same procedure of Newton's laws, except now we're under the understanding that we're going to use static frictional force when not in motion. And the other understanding is that static frictional force is a variable force. It depends on how much force you're applying because it needs to add up to 0 in order to not be moving, right? All the forces do. And then when an object is moving, we apply kinetic friction, and it's a much easier scenario to understand. You're just going to complete Newton's laws accordingly. So in this previous example, what is the frictional force if the crate is at rest on a surface and a horizontal force of 50 newtons is applied to it? What's the frictional force? So we have our crate, we of course have our normal and our weight, and now we have only a 50 Newton force pushing or pulling on the crate. And then this is our static frictional force. So we're going to apply Newton's first law. And we see that the static frictional force is going to equal 50 newtons. So right, the static frictional force is variable. It's variable until it reaches a maximum, and that's when you start using the kinetic frictional force. And so the static frictional force depends on how much force you're applying in that direction, right? It's simply going to be equal to the force that you're applying because of Newton's first law.